Hello everyone, and welcome to a very short discussion of general rotational motion of a rigid object rotating about a fixed axis. Basically what we're going to do today is take that motion that we've looked at rotationally. We've done constant angular velocity, and then we've done uniform angular acceleration, and now we're going to go into general rotational motion, which basically means we need to talk through the derivatives. Once again, you should always be keeping the linear analogy in mind because it works the same way in rotation. For example, as with the linear motion, right, we can define the average angular velocity, omega, with a line over the top, right, means average, as the change in the angular position over the change in the time. Graphically, this would be the slope of a line connecting any 2 points on an angular position time graph. Right? This is the slope of that graph. So connect any 2 points on there. Now this is just an average value. If we want the instantaneous value, we have to, of course, shrink the time interval, right, which will make the chord a little bit better, a little bit better, a little bit better, until we get to the slope of the tangent line, right, which would be the actual instantaneous angular velocity at that time. Of course, mathematically, that means what we really need to do is to take a limit of delta theta over delta t as delta t approaches 0. Hopefully all of you by this point in the year are a little more versed in limits and in derivatives, right, from your calculus classes. Of course, taking the limit as delta t approaches 0 is really just taking a derivative. Right, so the instantaneous angular velocity is the derivative of the angular position with respect to time. So assuming that you have an angular position function of time, right, the angular position is a function of time, you can take the first derivative and get the angular velocity function. And you can evaluate that at any time t. Next step, average angular acceleration is the change in the angular velocity over the change in the time. Graphically, the average angular acceleration would be the slope of a line connecting any 2 points on the angular velocity time graph. Right? This is a slope, a rate of change of angular velocity with respect to time. Right? So if you take any 2 points on a graph of angular velocity versus time, the slope between those is the average acceleration. Note the line over this alpha. Of course, if we wanted a better value, approaching an instantaneous value, we would shrink delta t smaller, smaller, smaller till we get the slope of the tangent line, which is, of course, a limit as delta omega over delta t as delta t approaches 0, which, of course, is better known as a derivative. Right? So the angular acceleration as a function of time is equal to the derivative of the angular velocity with respect to time. Or this is the second derivative of the angular position function with respect to time. Right? Again, hoping you're just seeing this just like we learned with linear, right? And all the calculus you've done at this point. And that's really how far we go. They don't do a lot of this on an AP test, right? But there might be a few little things, which is why today's worksheet is rather short. It's just a front and a backer. Right? Although it also talks a bit about angular accelerations and some other things, linear accelerations of rigid objects rotating about fixed axes. Of course, we can go the other way as well. Right? Given an angular acceleration as a function of time, right, we can take an integral of that with respect to time and get the angular velocity. Take a definite integral between definite limits of integration, and you get technically the change in the angular velocity. Take an indefinite integral, as it's written here, and using some sort of initial condition, the angular velocity at some time t, right, that you can evaluate to get the constant, you can then actually find the angular velocity function. Likewise, if you have the angular velocity as a function of time, you take its integral with respect to time, and you can get the angular position function. Take the definite integral between definite limits of integration, right, of the angular velocity with respect to time, and you get the change in the angular position, otherwise known as angular displacement. take an indefinite integral of the angular velocity with respect to time, and use an initial condition where you know the angular position at some time t, so that you can figure out what the constant is, and you can get the actual angular position function, right, as a function of time. So derivatives to go from angular position to angular velocity to angular acceleration, integrals to go from angular acceleration to angular velocity to angular position. Again, just like linear. And this is all for describing the motion of a rigid object rotating about a fixed axis.